Yeah, hey, I'm Bruno Knychalla. I'm founder of Additive Tectonics, which is basically a spin-off of a big 3D printing company called Fit AG. We founded this company in 2020 in the middle of the pandemic, and it was actually quite good because it was kind of like a small enclave, and we could really focus on doing a construction startup in additive manufacturing, yeah. And because we have this big mothership behind us, we basically have a lot of experience in 3D printing. And yeah, we'll explain a bit what the problems are when you try to scale this up and if you try to make it construction relevant. And then also, construction brings in these problems of sustainability that I will talk a bit about it. But one of the big problems that we have is actually that, to do additive manufacturing, you kind of have to work digital. And the construction sector is the second least digitized sector in the world, but we managed to get to be better than agriculture and hunting, which is pretty good. But it still looks pretty grim for us, especially if you want to also work with AI technologies and these kind of things. You kind of have to be digital to start. But in Germany, where we are right now, which is also a big hub for 3D printing, it doesn't look as bad. Like here, we are at least in the green field here. But we have another problem, and that is that the government is not at all digitized. And this brings us also big problems, actually bigger problems than the construction thing. Because we are actually in construction, we are additive manufacturing that goes into construction, and this is quite exciting. So what we do is we work on developing the future of construction, architectural 3D printing, and I hope we all agree that it's at least part of the future of construction. And we do this by actually putting additive manufacturing at the center of process design and product design. I will talk a bit about what that means. So it's not just about the 3D printing part of it. You have to also design the processes before and after to be able to make products. And of course, you have to design the products because an architect right now, a classically trained architect, can't do this. And we do this in an environment that faces big issues. We talked about this a lot, so I will be quite quick. We generate huge amounts of waste. We don't have a lot of people on the construction side, at least in Germany. Like people don't want to really go into this environment anymore. And then when you start to digitize this thing, it becomes complex quite quickly. So methods are lacking to actually bring this complexity from the digital realm into the physical realm. And then also through modernism, we basically ended up with a pretty monotonous way of doing architecture that hasn't been done in other styles before. So these are the key issues, and we also have to kind of emancipate away from modernism to actually be able to apply these technologies in a correct way. And we at Additive Tectonics, we do it in a co-design cycle. It's kind of something that I caught off in Stuttgart, where I studied under Ake Menges. And so in our team, we are very interdisciplinary. So we see it we have the computational engineering, the design, additive manufacturing, but we also develop construction systems, for example, with Autodesk. And also our own material systems and the cybernetics, which in this case means how our machines communicate with each other, what type of silos you need to actually be able to industrially additive manufacture on the scale. And we need to do this because additive manufacturing is super complex. Like if you look at all of the parameters that go into, that you kind of have to control to make a manufactured part, you see that these parameters are very, very tough to handle, especially by only one profession. So this is why we assembled a quite interdisciplinary team, and also pretty young team, because it is kind of a young people's discipline. And you can see that we grew quite a lot. So here you see 14, we're actually a bit more. And I'm super happy to tell you that half of us are actually here. So if you have specific questions for specific topics, I'm happy to also introduce you all of the experts in these fields. Okay, so what are we doing? We actually focus on 4 main topics: metals, concrete, or let's say hydraulic binders, wood. So basically all the big construction materials, and of course automation and computation. I will just start with additive concrete, and then we can talk a bit later about the other things. So additive concrete, for us it started at TU Munich, where the selective cement activation technology was developed. And we had in the lab like a 50 by 50 by 50 kind of SCA printer. And this technology works with mixing aggregates and the binder inside a powder bed, and then you just activate it by basically jetting an activator on this on the particle bed. And the interesting part here is that we can be quite precise. We can be up to millimeter precision, and this is for like concrete or cement manufacturing pretty insane. What was lacking was the size. So we basically teamed up with a construction machine company and scaled up this machine. So our print bed is 10 cubic meters, like 4 meter by 2.5 meter by 1 meter. And it is the first and only type of its, like it's the only machine that exists in the world right now that is that big, that fast, and can print with construction material. Because this is also important, because you have binder jetting technologies, right? But most of them are not made to work with construction materials. And if you then go into the route of getting a permit to build, you need to kind of work with construction materials. And this machine is also super fast. We kind of range between 6 and 9 hours for 10 cubic meters. So I will tell you later on parts what this actually means. But one very important step I learned at TU Munich is that 3D printing basically closes the digital chain. So you can have a completely digital process to make a part and put it into reality without having a big margin of error and a lot of human interference. So this closing the digital chain is quite important if you want to bring your parts from BIM out into reality, or from a computational framework into reality. Okay. So here you see a prototype of a facade system that we developed for a project in Regensburg. And this was supposed to be 3,000 square meters of facade. And it's basically just a fancy shading, and I don't want to talk really about the architecture behind it. I'm just super proud to say that a thing like this you could fabricate in 2.5 hours. And this makes 3D printing suddenly become construction relevant, because you have to calculate the costs up to your machine capacity. And only if you scale it up with speed and size, you're actually able to be a real player in the construction field. But for us it wasn't really only about the aesthetic possibilities that we have. We also wanted to integrate functions, and we know this from 3D printing, right? Our volumetric designs, our internal structures that help us kind of steer the function of a construction element. So we wanted to boil it all together to get multifunctional building elements. And there we teamed up with TU Munich, and Dirk Loke was telling a bit about it. I just want to show you the video and talk a bit about it. So it was inspired by Marcel Breuer, who is basically a modernist architect and designer. And we, for the first time, wanted to see if we can really functionally integrate building functions into an element. And you saw that we also analyzed like how the heat is being transported through our elements, and how we can actually use these structures inside of the element to gain a benefit, in this case in insulation. You have the solar potential of self-shading, and a lot of other interesting principles that can be solved with additive manufacturing, especially also the curvature. And in my opinion, it's the first time that you can really see additive manufacturing being applied like a prefabricated building element that has a certain extra value to it. So in a new recent paper, you can actually read on why we chose certain structures. It has to do also with our depowdering process, because after the print, basically this part gets taken out of the machine in a big box, and then you have to suck out all of the unactivated material, and you use this in the next phase, in the next print. And this unactivated material is in these cells, so we have to get it out. And it was the first time that something this big and this high res was actually printed in concrete, like it's standard Portland concrete. And there you have some problems with baking. The material basically bakes inside and it's really tough to get out. So we are really working on this, but you see that, in my opinion, it's already very convincing, even though it was our first real prototype that we did in cement, in standard Portland cement. Of course, you could use other binders, but we wanted to have something that's very available, and we wanted to see if we are able to actually build an element that's this size in one go. So this element took 9 hours to print. This has to do with the compressed material, and the water tends to penetrate slower than with other materials. So it's actually our slowest print. Like, we could also do this in 6 hours, but with other materials. And you see that in the back, it's reinforced. Yeah, and of course we also did other projects. This is an art project. It's supposed to be a blood cell. And this is just the smallest piece. We actually did a very, I think, 5 times as big piece like this. Like, these are the small projects that you kind of have to do to validate your technology. And then there, I don't know if you see where the 3D print is. It's quite hidden. It's these mushrooms. There you also see a bit our facility, how it looks like. The problem is right now that we are facing is that all of them broke. The mushroom broke, the blood cell broke, also the big element broke. And this has to do with microcracks that happen when you unpack these parts. And this we could only know by doing it big. So there are effects that happen, like you have microcracks that make you be able to handle the part, but as soon as it's outside, these microcracks kind of tend to widen and biggen, and then the part fails. So this is the stuff that we kind of right now try to figure out, like really going into projects and see if we are able to realize this project and learn from them and adapt them. Okay, Portland cement, pretty complicated. Wood. So with the last projects, we developed our own printing material, which is kind of expanded glass from bottles that had their life cycle basically extended, because these bottles normally just have 5 cycles and then they are trashed. And we basically use this old glass, and there are companies that make expanded glass out of them, and we tailored the material together with cement to be able to get a 3D printed material out of it, out of basically recycled glass bottles. And Patrick did all of the material tailoring, gathered all of the data that we had to get to actually know if we are able to print such a large element with it. But in this process, we also noticed that we can do a process like this with a lot of different materials. So wood, chippings, brick, sand, limestone, a lot of possibilities. And we were like, wow, this is really something. Like, you can use waste materials, local materials from everywhere and print with them and make real construction elements in speeds that are relevant for construction. But then reality hit again, and we looked at our setup that we developed during COVID. Like, basically you see these brutalist buildings are silos, and they stand on sensors, and you have a mixing and material pumping station in the middle, and it's constantly supervised. And if you have to do it like this if you want to do an industrial machine, an industrial setup. But then, once you have it industrialized, it's pretty tough to react on all of these different materials, because your machinery might not be able to like all of the little chippings and different sustainable materials that you want to work with. So we had to focus, and we focused on wood. So what you see here is a material that we call Econit wood. It's a magnesium wood hybrid. Basically, you have beech wood chippings inside, and you bind them by using magnesium oxycement and magnesium chloride. The interesting part here is that you use this binder, this magnesium binder, also as a flammability retardant for wood. Like, in German we call it Sauerkrautplatten. These plates are made of wood, and you use these magnesium binders to actually protect them from fire. So our binder doesn't just bind the wood, it also makes it fireproof. And we are right now elaborating the acoustic properties of them, but it looks pretty good. And the interesting thing is that If we fill the machine with acoustic plates like this, where every plate could be different, a plate like this, 50 by 50 centimeters, 2.5 centimeters thick, would be 40 seconds to fabricate. So suddenly we are in a range where additive manufacturing can be scaled and can be applied to construction. Okay, so technologically it's possible. The problem is that everybody comes to you and says, let's 3D print this, let's 3D print that, let's do an art project, let's do something really crazy. But this is not how you make money. This is not sustainable. So how you can actually bring this power onto the streets is by making products. Products that need additive manufacturing, where you actually develop the whole process from the design to the finished products. Yeah, so we are in the process of doing that. I have to speed up a bit and develop basically these acoustic products. But there's of course a lot of other potentials with this wood, with these wood products that need to be explored. And if you want to do this, if you want to help us making products out of 3D printed wood, we are happy to work with you. Especially because this biomass doesn't need to be beechwood. It can also be something that grows quick, that harvests a lot of CO2 from the atmosphere. Okay, let's talk about metal. I really have to speed up. So an artist group approached us and wanted to do a big altar project, and they wanted to do it in WAM. And we, together with our mother company, we know how to do WAM, and it would have been 5 times the costs that the artists expected. So we came up with a different way and used basically an SLS print and sprayed aluminum around it, did a lot of material tests. And so basically it's an interesting load case where that's kind of made up, but kind of also made so that the structure has a certain aesthetic. And then there you see how we spray the aluminum around it. The aluminum is there to really reinforce it. Like we calculated the project just with the aluminum skin around it. And then we assembled it by hand. And you see that it's a very complex puzzle, like 60 different pieces, each individual. And there you see the finished part in the church. And it was actually, the Cardinal Marx came and praised it. I don't know what's in English. That was quite interesting. Okay, so the last topic is computational automation. I will just tell you a story through a project. It's again an art project where we do FDM together with an artist called Peter Lang. He is a landscape painter, and he normally paints layered paintings. Like he makes very straight lines by snipping a string on a surface. So we said we actually do the same thing. You just have to learn how to model. He didn't want to learn how to model, so we made him a VR interface where he could actually paint his layers. And we made a custom setup for a museum where you could color on the go these prints and would basically give in the color code that he decided before in VR. So he was 800 hours in VR, and we printed 800 hours in Hannover. And actually, it's not just a coloring system for us. For us, it's a way to actually make a new material on the fly. Like you could grade a material, you could use 2 different materials. And you see that this is quite big. And for us, it was intense because we printed it live in a museum, which makes you ready for industrial fabrication. Okay, but you see we overheated the material a bit to get an artistic finish. But we worked together with a company to also do it properly, to make products out of it. We know how to color things, so we use our wood material. Like the whole structure that you saw is basically a lignin-based polymer. And we right now develop a range of products for these people that you might know. Yeah, and we are quite excited to kind of go in the range of products. And of course, we want to push architecture, but to do a startup means you kind of have to start selling things on a consistent level. Okay, so we do very interesting stuff. If you're interested to follow us, feel free to scan the code. And yeah, maybe if you have ideas for our new wood material, I would be very excited to work together with experts in the field. And I'm happy to be here. Thank you.
Thank you very much, Bruno. Are there any questions from the audience? Well, then I get to start with my question. You were talking a little bit about the demonstration that the project represents. We're talking about pushing architecture. In my experience, it's as much about pushing additive manufacturing into architecture before you can do it the other way around. I was wondering how you look at the projects you work on, how you choose them, how you work on them in that light of kind of using them as demonstrators to push the technology further into the industry.
Yeah, it's a very good question, and it's actually very tough to choose the right project, because we also know that we kind of have to stand behind the projects, especially in the beginning. So a lot of projects we don't show, but we still want to do them to test it. So we basically show the stuff that we like, but there are a lot of projects in the drawer where we are not so happy about showing them. But for sure it means getting the right architects to work with you. Architects that know about 3D printing, and there are not so many, especially in the established field. So I'm counting on you guys.
Thank you.
Can you explain me why we saw the same project in the morning in a DFG basic research funded project and in the afternoon in an industrial research?
Yeah, I can explain. So basically this technology comes out of TU Munich, like the SCA technology. The SCA technology was developed at TU Munich, but the machine development and the process development happens in AT. But of course there are very crucial steps to scaling this up that a university has really troubles to research on, and this is where we come in. And a university would not be able to have all of, or for now, I don't know, maybe it changes now with this big funds that are coming into. Yeah, we work together with them to realize the project. We also were part of the papers that are being written and these types of things, because there is a lot of knowledge that you get from scaling it up, and universities tend to start small. Yeah, and we are, I think, more unrigorous, but more, how do you say? Yeah, we just do it, and then we tend to first do it and then check if it worked, instead of over academicizing a problem.
Thank you, Bruno.
There's the question about your mushroom failure story. So do you have any solution, or you won't ever print any more or produce any more mushrooms? That's the thing.
So the mushroom was an art project. Yeah, we think we have a solution, but we first have to test it in small scale, actually. But we noticed these problems by scaling it up, and we will continue with Portland cement. From an academic point of view, it might seem super simple, like a super tiny problem that you can solve. The problem is in an industrial setup, each little problem that you try to solve means a lot of costs, a lot of extra costs. And we are right now not sure if we can sustain the process how it is right now and solve it. So, yeah, a lot has to do with the green state of the Portland cement. Like you print it and then you leave it 4 days in the powder bed, but then you have to unpack it, otherwise it dries and gets cracks from drying. So you have to take it out of the bed in a green state, and this is where the micro cracks happen, we think. So there are ways to solve it. Some have to do with fibers, some have to do with different post-processing methods, but it's 5 different solutions, so we have to check.